Hello, this is Mark Anderson. Welcome to my talk on deploying DOE to accelerate R&D for biotech. If you're able to see the slide and hear me speaking, on your control panel, there's different signals you can put in. There's one that has a hand on it. If you press that, it goes up and I can see that I'm getting through. All right, Niels, thank you. Catherine, etc. Okay, great. I've got a nice little sampling out of the group that gives me some affirmation that the wonders of the internet are working again, amazingly enough. So I'll go ahead and start my show from this point. And again, I'm Mark Anderson, and my background is chemical engineering. I'm also a certified quality engineer, and I achieved my MBA. I've had a broad range of working experience ranging from research and development in specialty chemical R&D, plant process improvement using my certified quality engineering skills. And then when I got my MBA, I started working more in product management, general management. Over the many years I've been with Statis, I ran the company, but then in recent years, I've scaled back to less than full-time. And now I'm back to my roots as engineering consultant, and very happy to present tools of design of experiments as my main job nowadays. So again, welcome. I'm going to keep attendees on mute throughout the presentation, and instead, ask if you would either come in with chat questions, which I may or may not catch along the way, but I'll look at afterwards, or you may just send further questions to me directly at mark@statis.com. By the way, this presentation is posted or will be at this site, 3wstatis.com, and webinars. So one more time then, if you would just press that raise hand button, make sure that you're with me and I'll be double certain. Okay, great. And I'm getting some others coming in here, Julia, etc. Okay. Thanks again, and I'll be looking for some feedback from time to time just to make sure I'm not just speaking into the void, so to speak. Okay, so the first thing that I always like to talk about is just a very high-level view of design of experiments. Some of you may not be doing too much yet with this tool, and others are doing some work but would maybe like to advance their skills. But my main focus as a chemical engineer was working on process development and plant process improvement. And in that role, I would be looking at what I called a unit operation, something I could draw a box around that I called the process. And then within that box, I would then, focus on first principles. And just to, put a name in the box, one of the things I did early on is I worked on natural vitamin E derived from soybean oil, which was readily available to General Mills, my employer. And the particular step that was most important was the crystallization. And this was to produce a very pure succinate form of natural vitamin E, which is, I think if I recollect correctly, it's been a few years, but I think it's a D-alpha tocopherol. So the natural has got the handedness, and so the D is the part that is most efficacious for people. So of course, the first goal was to maintain purity as we went into this final step of crystallizing, but our primary goal was to improve the yield. So I always advise, once you identify your process, this could be a product, and we could be talking about some kind of a mixture design. So process or product or any kind of a system, but I was mainly working on process. And then, the people that we work with, yourselves, I'm sure, are very highly trained academically. So you need to go back and think about first principles of what's going on. And in a case like this, of course, heat transfer was really paramount. But if I was working on chemical reactions, then I might be thinking about kinetics and things like that. Now, from these first principles, we get ideas of what factors we might include in a planned experiment. These have to be factors we can control. And obviously, in a case of crystallization, we needed to reduce the temperature to form the crystals. Temperature was a key aspect. Surprisingly, agitation rate. So this is just my examples, but you have your own situation to consider. What is it you're going to focus on? What are the responses that you can measure? What are factors you can control? And once you get that all together, then we can consider doing a design of experiments. And what we're going to do is a series of tests, and these are going to be groups of runs, okay, that have different conditions that you're testing. And typically, I would advise you have at least 8 runs per test, okay? And so we'll do a series of them, and we'll gradually fine-tune things by making purposeful changes to the input factors. And I emphasize the word purposeful because it's tempting to just go back and take production records or records from R&D and just do a least square regression on that. However, then you don't get good properties on the test matrix. So doing a proper planned DOE is essential, particularly since it'll help you identify the cause and effect relationships. Now, there's one caution, and we want to use statistics to be sure that we only react to things that are significant. And I would advise the P less than 0.05 rule. I think it's very good for design of experiments. So that's kind of the basic idea of it. Now, what we get from a designed experiment is a model that predicts the responses of each one of the things we're measuring, purity, yield in this case. So I'll put this down as Y for the response measure with a hat on the top, which indicates the predicted value for any individual response, I sub I. And then we get this function as a function of x's. This function could take different forms. It could be a linear, it could be a second order function like a quadratic equation that's used for response surface methods. It depends on, the layout of our experiment to begin with. But these models are very important, and they allow us to predict, for each of the individual responses at any given setup X, what's going to happen across the board. And ideally then, if this all works out very nicely, we can hit what I call the sweet spot, where all the requirements are met. And this has been a very effective tool for industrial R&D in particular, to some extent for plant process improvement, but it's a little harder to do experiments at that production level. And for all kinds of things, but my main focus is the industrial R&D, the research and development of processes and products. This is a very important tool for the biotech industry. And I've seen a tremendous amount of activity. Many new clients are coming in all across the board, whether it's biopharmaceutical or other types of biotech industries. It's very strong right now. So to give you an example to start with, we'll begin with the most simple type of DOE, which is called a 2-level factorial design. And these are very good in particular for process screening and characterization. And the example I'm going to give you is where we're looking at the shelf life of this biopharmaceutical product or what have you. And the goal was to get a doubling in the life from an accelerated test. And this was an actual experiment. It was done in Sweden. And the experimenters really needed to get the life doubled. They were currently running at 17 hours of shelf life. So they did their job in terms of the careful scientific method, which is called one factor at a time. And they started from this baseline, and they thought, surely factor A, if we increase it from a low to a high level, which I've coded as a minus for the low and the plus for the high, that it would certainly provide the answer they needed, which was 2 times 17 or 34 hours at least. But unfortunately, though it increased the life, it wasn't enough. And so they then had to go back to the drawing board and consider a second factor, which they thought, well, maybe factor B would work if we increase that. It actually did slightly better, but not good enough. And all they could think of then was one more factor, C, which they increased. And they got a very slight increase, which actually was surprising, but not enough. Well, luckily, the engineer working on this heard about a fellow named George Box, who's very famous in the field of DOE. And George Box actually inherited know-how about DOE as the son-in-law of Ronald Fisher, who invented the two-level design and industrial statistics in general, and became knighted by United Kingdom for his work in the fields of agriculture. So Fisher developed these two-level designs. Box carried it forward with more advanced techniques like response surface methods. And he migrated from UK to University of Wisconsin, which is just across the river from where I live in Minnesota, where I'm located. I actually took training from George Box at University of Wisconsin myself in the mid-1990s. So the experimenter traveled to Wisconsin and learned about these two-level designs. And George said, why don't you do 3 factors, each at 2 levels, that forms a 2 to the 3 power, which is 8 combinations. And lo and behold, they found at the combination of A and B together, which is an interaction, that they got their breakthrough in terms of the product shelf life. So this is a really good example of how the multi-factor approach is far superior to the 1 factor at a time, or OFAD, for the reason that it can detect interactions that would never be seen from the simple 1 factor at a time approach. Now that is enough already, hopefully, to make people realize that this is how we need to go once we get close to our goal with the multi-factor testing, and for process a 2-level design is perfect to begin with. But also these test matrices are set up in a very clever way that embed averaging, and with this design, which is simply just all the possible combinations, we actually end up with 4 at each of the high levels of each of the 3 main effects. Like A has 4 at the right that are high and 4 at the left that are low. And of course, if you consider the cube here, we've got the top versus the bottom, that would represent the effect of B, and the front versus back would be the effect of C. But we also embedded in this get the interaction of AB, which turned out to be the key, 4x4 comparison. AC, BC are 2 other 2-factor interactions that we can estimate. And the 3-factor interaction, ABC, also can be estimated, although usually that doesn't turn out to be very significant. So coming back to the OFAD experimenters and confronting them with this and saying, look, if you do just 1 of each, that's very poor. And they say, well, we could do 4 at the baseline and then do 4 at each of the high levels. Now, at least we would get the main effects estimated from this on a 4x4 basis. But of course, we now have 16 runs for the OFAD versus only 8. So we have this efficiency of 2 to 1. So this is kind of my quick pitch in terms of getting people started on DOE. And let me just ask you, is that compelling to you, the advantage of 2-level design versus OFAD? If so, press that raise hand button. Okay, Julia and others are with me on this. Kanan, Merrick, etc., and Val. Great, perfect. Okay, because I need you to be on board for this idea of doing multi-factor testing if you're going to buy into the idea of using DOE for the biotech, type processes. There's also similar types of designs, but they're structured differently for mixture experiments, which I'll get to later. Okay, so that's my initial starting point. Now, what happened here was Fisher, which is 2-level designs, covered the first 2 steps that we recommend for a good strategy of experimentation, which is to first do a screening on many unknown factors and do something that's broad and shallow. And one of the experiments that I might suggest here would be to do, let's say, 16 runs. I think is a good number of runs for any given experiment. But we could put as many as 8 factors in and do a design that's fairly broad and shallow. Now I'm going to open up my tool, which is Statis software, Statis 360. Statis 360 is a more advanced package. The base package that's embedded within Statis 360 is called Design Expert. And Design Expert might serve for most of the group that are working in industrial engineering. But if you're more advanced as a data analyst, the 360 offers this very powerful Python scripting tool. And some of our users are very interested in that. So either Design Expert or Statis 360, you would begin by going to this design builder, which shows the full combinations of things along this diagonal. But as you get to 5 or more factors, you can begin doing fractions. And as a starting point with the standard design builder I have here, I might, before I press ahead with what the chemist gives me to scale up, is say, well, look, what are some other factors that potentially could affect this process that maybe you haven't tested before? I would lay those out, and maybe I would do as many as 8 factors in 16 runs. Now we notice we go from the white to green. Green is a higher level resolution that is good for characterizing two-factor interactions. But if we're just trying to screen, we can continue to fractionate all the way back to this point here. So the yellow is proceed with caution. But also you see red designs. These are designs I wouldn't recommend for any development purpose, but only for what's called ruggedness testing, where you're just trying to make sure the process or test method or product will continue to operate in the field. So these designs that are red have too many factors and too few runs to even get a good estimate of the main effects. So this strategy is very important to first maybe go back and look at previously unknown factors and try to screen down with a very broad and shallow design, which are going to be yellow on our design builder, and then see if there's a vital few main effects that might have been overlooked or factors. So we're going to generate main effects. We're going to see that those factors, probably should be included in the next phase, which now is going to be a higher level design to characterize the two-factor interactions. Now these designs, we need to do fewer runs or fewer factors. We need to get to one of these green designs, and this is one that I would recommend at this stage, which has got only 5 factors instead of 8, which gives us a higher resolution with the 16 runs. So now I'm going to say 16 runs again, but now scale back to 5 factors. And this would allow us to detect the interactions of things. And I also advise putting in center points. And this can be done very easily with our program. For example, up here I can say I want to do center points, and I can set up a little experiment, with the factors that I'm interested, like in my crystallization. I can put in things like temperature and agitation rate and all those good things. And then, the units of measure, back then I was working in degrees Fahrenheit, and this would be RPM and so forth. We can also put in categorical factors, that's not a problem. So we could have one type of thing versus another, one type of reagent that we're crystallizing from versus another. And then after we put these numbers in, I can't remember the temperature, so I'm going to put in something below freezing, but this is probably not right. Something like this, and then whatever the agitation rate is. So you can see how easy it is to set this up. And then I'll leave the other ones at the -1, +1 coded levels. And then here's where we're going to put in our responses that we're interested in measuring, like yield and purity of the product. All right, and then we finish up and we have a design that's laid out in random order, and embedded in this are a series of different conditions that are at the center. So you can see how easy this is using the Stati software. So these would be green designs, or they would be the full, which are white on our diagonal. But now I have the center points in, I can test for a curvature or nonlinear behavior. If there is curvature and it's important, significant and important, then we're going to switch over to something called response surface methods. And this is where Box came into play and invented a design that's called a central composite design, along with a fellow named Wilson in 1951. And so things progressed to the optimization phase. At that point, Fisher's work was done beginning in the 1920s. And then last but not least, either we skip this RSM step if we don't see curvature, or we go through it and then we get the answers we're looking for. Then we have to do some kind of confirmation run. And this is where the red designs come in for what's called ruggedness testing. And these would be red designs, which are very small. We can also do a flavor of designs called Plackett-Berman, which is actually very popular in biotech. Unfortunately, it's misused for development purposes because these designs are very low resolution, and I really would only use it at the end for ruggedness testing It's better if you're going to do screening and characterization to go with the higher resolution 2-level designs. Okay, so this gives you a good strategy of experimentation. It's also known as the SCO strategy, a la DuPont, that took these techniques in the 1950s and really grabbed a hold of them and made this kind of the way that they did their R&D. And I like to put a little R at the end and call it the SCOR, or SCORE strategy, because I do think doing the ruggedness testing at the end is probably good. And if you're interested in that, there's some other webinars that I've presented, and you can go to our website and kind of look through the different webinars on our YouTube channel, and you'll see more information about the strategy. Okay, now what I want to do is focus on this first part, which is the screening and characterization. Okay, so the idea of this is to quickly sift through a large number of potential factors, discarding the trivial many, and then following up with an experiment that focuses on the vital few. And so we're going to use what are called fractional 2-level designs, and these are going to be fairly highly fractionated designs. These are going to be the yellow designs that we saw, and then to follow up, we're going to do either the full factorial designs or the lesser fractional green designs. And at this point, I just want to, check back with you guys. Does this make sense to apply a strategy like this from your perspective of, developing a new process or product, going back and maybe looking at some things that haven't been really studied properly, just in case there's maybe a few that have been overlooked, and then do the more in-depth study? If that makes sense to you, I'm just going to ask for some positivity back on the control panel. And part of it is I just want to make sure that I'm still, connected up here, since we're working at a distance. Okay, thank you, Val, and others that are responding. Good. So then, because we've got just a short time here, I want to make sure we continue on and cover some more things. So I'm just going to give you a quick overview of a 2-level design that was actually done in the biotech industry by this fellow, Aaron. And he came to Statis, he had our Statis software, and he said, I really want to improve the yield of this pharmaceutical that's made via recombinant E. coli fermentation. And there's a number of factors that I would really like to study. There's 6 of them: the temperature and the medium pH of it, the amount of oxygen dissolved into it, the amount of cells we load up, which is measured by optical density, and then 2 different solutions that are used as a feed for these cells. And I'm not familiar with what exactly these are, but you might be able to pick up on some of this from this posting, from the publication of this in Bioprocess. So the goal was to improve the yield, which was measured by the optical density. So we got our heads together and we thought about, what we have with this design builder. This is a slightly older version of it, but it's still pretty close to what we currently have. And with 6 factors, Aaron felt like 64 runs for the tool, full design, or 2 to the 6 power, would be way too many. And I tried to talk him into doing 32 runs to get this higher resolution, and that way you get clean estimates of 2-factor interactions. He said, no, I really want to get it down to 16 runs. I said, well, that might work. You possibly would get some information about the interactions, but you might have to do some follow-up studies to determine that. He said, that sounds good. And kind of a little joke here for the biotech is he said, that's a happy medium, he said, with only 16 runs. However, you are going to get 8 at the high level of each factor and 8 at the low, which is, certainly much better than the 8-run design. So I like the 16-run design, as a really good option. It's a nice sweet spot. Now, I won't get into too many of the details here, but just to say that when Fisher developed these 2-level designs, which we represent as 2 to the power of K, is kind of a shorthand speak for the Fisher designs, it really was laid out in a very, simple way, with the first factor going low, high, all the way down. The second factor, 2 lows and 2 highs. 4 lows and 4 highs for factor C, and 8 lows and 8 highs for factor D. Now, we don't want to run it in this standard order. We want to scramble it in random order. Otherwise, for example, D would be sabotaged if there's a time-related lurking factor like increasing temperature, humidity in the production environment, that type of thing. So always randomize the experiment. Now this layout is giving us 4 factors in 16 runs, and it has really good properties. We call this an orthogonal matrix because the correlation of any one effect with any other effect, R sub I J, is equal to 0. There's no correlation. So it gives you a perfectly informative matrix. However, we want to get 2 more factors into this to create the design with 6 factors. So there's some trickery involved, and the software will know what to do here and set this up for you to create the optimal fraction. So we don't need to worry about this detail here. It'll be set up by the program. All right, now already I'm cutting to the answer at the end, and I'll show you very quickly how this was arrived at. But this is what we call a Pareto chart. It's an ordered bar chart, and it shows that the induction OD, which is the amount of cells coming in, create a big impact on the cells coming out. So no surprise. But what was really interesting is there was an interaction of the temperature with the induction OD, and this was very significant. Because of the fact this was just a yellow design, there was a potential confusion that had to be resolved. But he was able to resolve that it was indeed the AD interaction. So let me show you how that can be done using the software. So I'm going to show you how this was built. And it started off like this. And we negotiated, Aaron and I did, and he decided we really would like to do only 16 runs, and we could see the yellow indicates, well, this is really ideal for screening main effects, but it's going to be not so good for the 2-factor interactions, but maybe not so bad. But then we also had a little brainstorm because Aaron said that he actually had a series of 4 fermenters lined up, and he could break this down into each one of those into 4 groups. And I said, okay, what you can do is what's called blocking, recognizing that we've got 4 different things and we want to correct for any variations between the fermenters. And so this, when I switch from 1 to 4, actually invalidates some of the designs that can't support this division into 4. But the design we were on was fine. So we pressed ahead with that, and never mind that screen, but that's important to understand what you're getting when you cut back so far. But like I said, basically then it's just a matter of typing in the names, units, the types, which could be categoric, the levels, which Aaron came up with. And then these are the block names. And so this would be fermenter 1, fermenter 2. And so we're going to end up grouping and dividing these out. And then the other thing is that when we put this response in, there was just one of them. I asked him, what would be the smallest difference that would be important to you in terms of the yield? And he said, well, if I could see even a 3% improvement, that would be a big payoff. So we put that into this field, which is difference to detect. And then I said, based on your prior experimentation, how much variation do you normally see? And he said, well, I think the standard deviation of the harvest might be, let's say 1.5. And this provides us with a power calculation that says it's very probable, almost 95%, that if there was a difference of 3, even though there's uncertainty because of the sampling, the fermentation process itself, and the measurement of yield, it's very likely that we're going to detect that difference even as small as 3%. And normally we suggest this be at least 80%. So this is a nice feature of the software for the 2-level designs. And then we create our design in random order. And these are the groupings for each of the different fermenters have different combinations of things, which we label as factorial. But we also, which is a nice feature, have each one of them doing one common condition, which makes it easy for us to compare from one fermenter to the next directly. This center point will also give us a test on curvature, which is kind of a bonus, and it can be used for what's called an estimate of pure error. So I like having this control center point embedded. Now the results are collected And then we could get into all kinds of things, but I just don't have the time to really do a proper demonstration of this all the way through. But I would suggest if you have the software already, or if you get it on trial, if you want to learn more about the two-level design, go to Help Tutorials and then do this two-level factorial tutorial. And it'll go through a lot more detail than what I can do in the short time I have. But this is a very effective tool for fermentation processes. For the screening and characterization, the first, two big steps in our strategy. So now what we're going to do is we're going to analyze the results, calculate the effects, all the main effects in whatever two-factor interactions we can. And then straight away, we get this view that the induction OD is the key. And we can actually see this pretty easy on a simple scatter plot without, doing a lot of work on this. If we look at the effects of the temperature on the simple scatter plot, not very much. pH, not very much. Dissolved oxygen, not very much, but there's an extremely strong impact of induction OD on the harvest OD. So that was kind of a given. We kind of knew that. But there's also, and you can see this on the specialized plot for picking effects, there's a definite impact of the interaction of AD beyond what we would figure from our trivial many effects that are near zero. And with the special y-axis, they line up. The next effect is temperature. Now, going back to the Pareto chart, this one I've got the lines on for the t-value limit, which is based on a p of 0.05, which is a simple comparative test, and then a more rigorous Bonferroni pairwise correction. But we can see how D itself towers way above, but AD also is even above this more conservative Bonferroni limit. And just a quick survey of the group. How many have heard of a t-test? And the idea of doing a t-test with, p less than 0.05. Okay, Val, anybody else? Quite a number of other people as well. So this is a very, common thing that I think, even people that are not very advanced in statistics, if they're working in R&D, they would have heard of a t-test, and most everybody knows about p-values, but these are more sophisticated tools now that are in the context of the two-level factorial design. So then, as far as the p-values are concerned, we can look at the f-tests on these overall model and individual effects that we come up with, and the f-test named after Fisher. And you can see that overall, this model is very significant. That includes temperature, induction OD, and then the AD interaction, which is the key. Now I'm going to include A, even though it's slightly above 0.05, because it's needed to maintain the structure of our model if we include AD, and that's called model hierarchy. So the program would ask you to please include A no matter what, but it is pretty important on its own. Then the software gives you these R-squared values. Don't use the raw R-squared. That would lend to over selection of model terms, but use the adjusted and predicted and other stats, but they're very good. The program also gives you a complete suite of diagnostics to make sure there's nothing abnormal. And this one follows a normal pattern of a specialized y-axis to plot. It just is on a straight line, which is good. And then I like looking at this one residual versus run plot to see if there's any outliers outside of the red lines or any trends and that type of thing. And then there's another plot, again, George Box was involved, called Box-Cox. And that one's good for seeing if a transformation might be helpful. Quite often on these biotech, involving cell growth, the natural log is recommended. But in this case, we didn't need to go to that. So here's the final result that was very exciting for Aaron and resulted in a huge breakthrough for him. They really wanted to get the loading of the cells up, but they weren't quite sure how far they could go with it. And they found that temperature became a very important factor when they went to this red line, which is the high cell induction, in that if they didn't reduce the temperature, they didn't get anywhere near the increase in yield that they would expect. So it was this interaction, the effective temperature depending on the cell loading, and up here is a clear winner where they reduce the temperature at the high cell loading and that's where they got their harvest up quite high, over 100. And we can actually use the program to just do a hill climbing search to verify that those are the conditions. I'm putting a stretch target at the upper end. And sure enough, it says, if you go to the low temperature and the high cell loading, then you're going to get your harvest above 100, which was a big improvement for Aaron's company, Diosynth. Now, over the ranges that were tested on pH, dissolved oxygen, the complex feed, and the inducer feed, they didn't have a statistically significant impact. So these are factors that you can set within the range at whatever seems most convenient for you, or to be conservative, just leave them at the original set points that are shown here. Okay, so hopefully that provides a good impression for you of the two-level design and one example for biotech. Now we have more modern designs that were developed after I did this study with Aaron back in the early 2000s. And these are called minimum run designs. And so they offer the chance to go up even higher in the number of factors. Or for a given number of factors with only a few more runs, you can do a higher resolution. So for example, in Aaron's case, we could have gone from 16 runs with the new structures of minimum run characterized from 16 to 22, and that would have saved him some follow-up runs that were needed to verify it was the interaction of the induction OD and the temperature, the AD interaction. You can also use these more modern minimum run designs to increase the number of runs for screening. So like if you get to 9 runs, then the best yellow design, which was invented by Fisher, is 32 runs. But you can do 9 runs in as few as 18, 9 factors in as few as 18 runs. But normally we recommend putting a couple of extra runs, so we've got a more conservative minimum run plus 2 option. So these are what are detailed on this table. So more modern techniques that were developed after the year 2000, the references are shown here. Okay, now response surface methods. Well, not a lot of people won't get to this level because it's going to require a lot more runs, and you're going to have to do at least 3 levels of each factor. But this would be used if you really want to get that last little bit of yield or product quality out, and you're getting right to the top of the mountain peak. So after doing the fractional designs for screening or jumping straight in with one design like Aaron did that kind of combined screening characterization, and you want to get even further, you might have to go to this response surface methods to get that optimized result. These are nice because they produce maps, really nice contour maps of 3D surfaces that can guide you to the peak. So I suggest using first principles know-how, screening characterization tools, and so forth, and then see if you can get into a zone, and if necessary, to get ahead of the competition. And if there's nonlinear behavior, if we focus this properly, we can fit a simple, what's called a quadratic model to our data. Now your design is going to have to do at least 3 levels of each factor, like here I'm drawing in these dots to indicate that within this square space, we're doing a design that has 3 levels of each factor. And let's say there's 2 factors, so we've got a total of 9 combinations that would generate what we need to draw this curve. So this is a very powerful tool, and when I was working on the natural vitamin E processing, I actually worked with a guy named Bill, who is a PhD organic chemist, and Bill was very strong on 1 factor design. So we had this goal of increasing the yield of the vitamin E, and Bill's made a very methodical series of levels here of factor A, and he said, oh, I think the peak of it is here. So he set A at that level, then he turned his attention to factor B because it's 1 factor at a time. And I said, Bill, I'm going to do something different. I'm going to do this 3-level design, which is a response surface method with the 2 factors. And I'm going to do a more thorough exploration of this space. And I'm doing a design like this, and then I'm going to do a series of center points to get more strength at the middle here. So now I've got 9 factorial combinations plus 4, or 13 runs. It's not very many. And from this, though, I can predict the response not only as a function of the main effects of X1 and X2 and the interaction effect, which we could get from a 2-level design, but I'm also able to get the squared terms, x sub 1 squared and x sub 2 squared. And so this forms this quadratic model. And from that, I could draw with the software this rising ridge. And I could see what Bill had done was he had got stuck on this point here at, let's say, 77% vitamin E yield. And I was able to get up to 95%. And this was worth $2 million a year for the General Mills chemical. So it's amazing how the multi-factor approach, when you get into these kind of scenarios, is incredibly effective for getting that last bit of improvement that you need to really make good money and beat the competition. So this is something that would happen after you apply your first principle subject matter knowledge, do some two-level screening characterization, get down to just a few factors, and then do the response surface method, measure the responses, do the least square fitting, and then we're going to use these polynomial models. And typically the quadratic is enough. So Box invented this, and he had a very good saying that all models are wrong, but some are useful. So it's an empirical method, but it can be very, very impressive in terms of the impact. Okay, so here's an example, and this is one that was done in another fermentation with Streptomyces saliccolor, and they were trying to use this organism to produce an antibiotic. There's a reference down here for process biochemistry. And they had two main inputs that they had reduced it down to, this oxygen carrier and glucose, and they had 4 responses to the antibiotic itself, plus these other things that they were aiming for to increase the biomass, oxygen uptake, and glucose uptake. So the design is shown here, and what we have is the factorial part of it, which is a 2 to the 2, and it forms a square. But then we add these axial points that go outside of the original square, and this is where we're getting the multiple levels and also leverage that's needed for the nonlinear effect estimates. And then, of course, we want to have some center points in, and this one had 3 center points. So those are the 3 parts of what are called a central composite design. And this is what the composite is, the composite of the factorial part with the axial part and the center points. Okay, so this is a very good structure for response surface methods, because what we can do then when we do the fitting is we can fit these polynomial models, and ultimately we can find a sweet spot. And this is very important, especially for biopharmaceuticals, to identify the quality by design space. So this design is done using STATI software, but we're now into the response surface side of things, and we're listing this as a completely randomized design. There's also designs where you can hold some factors into groups, like temperature, that are hard to change, which I'm not going to get into, called split plot, but we have more advanced structures like that. But this one just had the 2 factors, units of measure, the levels, and then we're going to project out of the square a certain distance that's ideal for the properties that George Box was looking for in the central composite. And we're doing this in just one block, but we could break it into multiple blocks. Here are the different responses. And then this is a structure in random order. So in random order, we've got different factorial combinations, center combinations, and then the axial combinations that are going outside of the original square. So each of these is run and the data are collected. And so now we've got the 4 responses. Now I won't get into the details of the fitting, but the program's got some very powerful tools for least square regression, and even it'll suggest, what model would be appropriate. And in this first one, we're using the full quadratic model, and we get a surface like this, which has got a simple maximum at the middle, which we can see in the 3D view. So that's our main thing, is the antibiotic. And then the other responses were also analyzed, and each one of them had kind of a different, surface that was created as you looked at each individual response. Here's kind of just a stationary ridge, and for the glucose uptake, a kind of unusual, more of a stationary ridge at the top. But what you can do then is at the end, you can say, well, look, I want to not only maximize my antibiotic and make sure it's above a certain level, let's say 50, and I'm putting a stretch target at the upper end, but I also want to increase biomass, and I've got a certain minimum level I want to get to there. And each of these goals are showing a desirability going from 0 or not desirable at all to 1, which is completely desirable. And then from all of this, we can do a multiple response optimization for overall desirability. And this is our result here in terms of what to set A and B at to get all of these maximized simultaneously. And even I could say I want to make the antibiotic reduction the most important thing of all, and then just leave these others at the normal setting of 3 for importance, and that would bias our results to try to get more of the antibiotic. Then from there, we can overlay each of these, and we can even put a confidence interval in around the outside to be more conservative, and you end up with a conservative optimum in a space, which we call quality by design space, that if I put these other confidence intervals in here, will be a really nice QBD quality by design space. It actually turns out to be very small, but there is a space here using the 0.05 for my p-value. And so this is really where you're going to be the most safe at this combination of inputs of the 2 factors. So hopefully you find that fairly amazing. If you do, if you think that's pretty cool, then give me a signal on your control panel again, and then we'll go down the home stretch on mixture design. Okay, Kanan and others. Thank you. All right, I've got, sorry, I've got so many things I'd like to tell you about that. I just don't even have the time to do it. So I'm having to work through this fairly quickly. But you can go back later. There'll be a recording of this, and you could take a look at that. There'll also be the slides will be posted. But I wanted to give just a couple of minutes here at the end to a type of design that I'm very fond of, which is mixture design for optimal formulation. And I think this is, greatly underutilized in the biotech industries. And I'm not sure exactly why, but I think what happens is people learn about these 2-level designs, and they're so fired up about that, and they learn about very fractional 2-level designs like Plackett-Berman's, and they just start using that on every single case. But very often, you're really dealing with what are really not process factors like time, temperature, agitation rate, as I use as a chemical engineer doing process development, but more the ingredients of the mixture. And this would be more of what you would do at the level of being a chemist, or some kind of biochemist, say biochemist. Oftentimes you're working with ingredients of a mixture. They're not really factors, although you can combine the mixture with process, like you could look at pH, but you could also look at a series of different ingredients. We have designs that can do that as well. But if you're strictly looking at ingredients of a mixture, like this young lady is interested in getting a milkshake, that has just the right amount of milk fat in it, and sugar, of course, and obviously chocolate has to be in there, and probably some kind of a thickener, like maybe guar gum. I used to work with thickeners with General Mills. Might go in there and make a nice thick milkshake for this young lady, and she's really going to like it. And what's going to happen is she's going to taste that, and like Shakespeare said, you don't need to eat the entire ox to know the meat is tough. Just a little sip will do, and it's because the taste is going to be a function of the proportions. It's not the amounts that you drink, it's just a little bit. And this is very common for many different types of industrial R&D situations where you're trying to optimize a formulation. Now, what we need to do is fix the total to try to create a situation that we can apply the mixture design. And this fixing of the total is oftentimes an issue, but if you can simply work, at least in the R&D environment, in terms of 100 weight%, that'll get the job done. So what happens is, though, a lot of people don't get to this mixture design side of things, which was pioneered by Henri Chaffee back in the 1950s, but they keep applying the 2-level designs, which is a little bit frustrating to me. So here I've got a scenario. We've got a graduate of the Statis workshop, which is modern DOE. Okay, so we've got this workshop that's really good for process developers. And here's a fellow that's graduated and it's getting hot out, so he's going to set up a lemonade stand and do a little experiment. And we're going from low to high level of lemons in his experiment, which is a 2 to the 2 power. And he's going from low to high level of glasses of water. But if you look at this carefully, spend some time on it, you would realize that there's something flawed here. If we're taking a taste of 1 lemon to 1 glass of water, and we're taking a taste of 2 lemons to 2 glasses of water, well, that's just a scale up of the recipe. So this is a very poor layout of the experiment. So what we do then, and you could do this in Design Expert if I had time, I could demonstrate it for you, but we do a 2-component mixture design. And what we recognize then is that the total is 1 glass. And therefore, as we increase the amount of sugar water, which is X sub 2, then the lemon juice has to be decreased. They're completely connected with each other or correlated. And we could do a little experiment on this. We could do a tasting of pure lemon juice, which would be fairly sour on a, let's say, a 9-point scale. Let's say we have a 1 to 9-point scale, which is commonly used in food and beverage. It's called a hedonic index. 1 is very bad and 9 is very good. Now the pure lemon juice is going to be, pretty sour. But if we go to pure sugar water, that's going to taste pretty good. But now what we do is we also do a run at the middle and we get an unexpected increase, which is that lemons plus water tastes better than either one alone. And we furthermore do some check blends at 3/4 of lemon juice, which is not as good, and 1/4 of lemon juice, which maybe is even better. And then we replicate some of these runs and we form a little experiment like this. From this data, and you can set this up in Design Expert, we can fit this specialized mixture model, which is called a Chaffee polynomial, which we provide in our software. And this polynomial is actually a quadratic polynomial, but it looks a little bit different. There's no squared terms, but it's actually quite easy to fit. For beta 1, we were going to put in the number 3 because that's what we get for the pure lemon. For beta 2, we're going to put in 7 because that's what we got for the pure sugar water. And then this is a positive term that recognizes this upward deflection. And for example, if it was 8, then if you multiply this times 0.5 times 0.5, which is the coded values at the middle or centroid, that's equal to 0.25. That would give us a delta of 2 in the middle, and then we could do our hill climbing search from this curve, and voila, we'd have the really ideal lemonade. And this is how this graduate would fare if he did the proper design. He would have the best lemonade in the whole neighborhood. So how does that sound? Do you like that idea of having a tool that would optimize your formulation like this lemonade? Yes? Okay, good. All right. So then I've got one last example, and we're down the home stretch of just a couple of minutes, but I want to point out that our space is shifting from orthogonal cubicle, square and cubicle space to triangular space. And these are spaces that I became familiar with as a material scientist when I started working on, say, formulating stainless steel, and they're ruled from the bottom at 0 to the opposing apex at 100. And then you have to keep turning this diagram around to read it from the other direction. So bottom to top is x1, right to left in this diagram is x2 going 0 to 100%, and left to right is going 100% for the x3. All right, now how many of you have heard of this? If you've heard of these trilinear diagrams, are also called ternary diagrams, and also known as phase diagrams, give me a hands up on your control panel. All right, so a number of people have seen this. Some are more advanced. I can recognize some of the names here. I've been working on these for a long time. But here's kind of a cool diagram that I use for my material science class. And what we have is chromium at one corner, we have nickel at another, and iron at the other corner. But once you know any two ingredients, like if we go with 18% on 100% scale of the chromium. We go up from the bottom to the top 18% of the way. I draw a line here. Now, the second thing I've got here is nickel. And on this one, I'm going from left to right 8% of the way. Now, you notice once I get these two lines, there's an intersection. And so therefore, now I can read off the iron right off the diagram, where I can just, calculate that by deduction. It has to be 74%. And this is exactly where we need to be to make really good stainless steel silverware. I call it silverware or flatware for the kitchen. Okay, so then this is very powerful for biotech. And then this last example shows you a case of hypothetical media development using 3 different synthetic medias, measuring the peak viable cell density in millions of cells. And the program makes this super easy with this mixture design. And you just enter in here. If you've got constraints that don't form a simplex, which is a triangle space, no worries. It'll pop you down to an optimal custom computer generated experiment within the space that you have. This one, we just kept it simple, and we worked it within the simplex space and just created a lattice that had enough density to fit all the way up to a special cubic mixture model. And then the results are collected. And then the fitting is done to the specialized Chaffee polynomial model, which is shown here. Now, we do have this extra 3-part term in here that turned out to be very significant. And this is like 3 different synthetic medias coming together and giving you the synergism that would be pretty delightful if you could do that. And we didn't see anything abnormal in the diagnostics, but here's the final result, which was very satisfactory, is that up here, we're seeing some really high results for the peak VCD. And then the program can, search it out for you, putting a little stretch target in here. So here's the suggested combination of things. And the only other thing I would suggest, another tool in our software, is that once you settle in on your combinations, let's say 0.42 for the first synthetic media, 0.22 for the second, and then the third will just fill in to add up to a total of 100% or 1, is I would do maybe 6 confirmations of this outcome and just do a series of follow-ups, collect that data, and hopefully it would fall within this prediction interval, and you could say, hey, we did pretty good. We found that needle in the haystack. All right, and then we could actually take this, I'm not going to bother with it, but we could do a graphical overlay. We could put in the confidence interval, and there's an example of a quality by design space. So that's about all I've got. I just want to refer you to the series of books of which I'm the prime author of. And the first 2 will be more for the process designs that are used to screen and characterize, would cover those tools. And then obviously this last one is for the mixture design, for the optimal formulation. So those are 3 books that are available from your favorite bookstore, Amazon or the like. And then I mentioned the different classes that we teach. We do have the modern DOE, which is for the process side of things. That's a 5 half-day course done at a distance on Zoom. We have a mixture design if you're strictly doing formulation, or if you've got a big enough group, we can set up a class that is customized for your needs, probably would include some of all of the above. And for that, you can contact our workshops team if you want to get a quote. Or just go to our website and you can register for the public classes. And then I have very exciting news. Our workshop team, led by Sherry Kraber, has developed a shorter series of classes. Well, each class itself is shorter, only 2 half-days, and obviously more intense. So if time is of the essence, you might consider this series of classes across the board here, and then this for the optimization, which is a mixture design. So do take a look at our website and you'll see the information about this new series of essentials. All right, that's it. And I don't have time to stay on for chat. Oh, well, you know, I think what I'll do is this, is those of you that need to get off, go ahead and take off, and I bid you farewell. If those of you that have put in chat, if there is any chat, if want to hang on, I'll just go ahead now and look at that. But again, thank you for attending this presentation on deploying DOE for biotech. And I really hope that one way or the other that you make the most from every experiment.